looking at this makes me hungry. These are chicken nuggets. I'm going to talk about a theorem which has many names. One of the names is, of course, called the chicken nugget theorem. Another name, which you may have seen before, is less tasty. It's called the Frobenius coin problem. Another one is also not tasty but useful. You may have heard of the postage stamp theorem. All of these are related to a very basic and important question that happens when you are only able to buy things in certain sizes. The chicken nugget theorem, I think, is how it's called by many people in the United States, because for some time it was only possible to buy chicken nuggets in boxes of one size or another size. It was actually 9 and 20, but that would make my numbers too difficult. Pretend that you are going to buy chicken nuggets, and the store tells you they only have 2 kinds of boxes. One has 7 nuggets at a time, and one has 10 nuggets at a time. If you tell them that you want to buy 24 nuggets, that's okay, because they can sell you 24 nuggets as 1 box of 10 plus 2 boxes of 7. If you tell them that you want 14 nuggets, that's also okay. They'll sell you 2 boxes of 7. But if you tell them that you want 19 nuggets, they will tell you you cannot buy 19 nuggets. The best you can try is to buy 20 nuggets and maybe give one to a friend. But 19 nuggets you cannot make from 7s and 10s. By the way, I showed the 14 example to say that it is okay to only use 7s. It's also okay to only use 10s. Why does this problem have so many different names? Well, because certainly people cared about this problem long before there were chicken nuggets. And postage stamps are the same thing. If you are mailing a letter and you put stamps, maybe you only have 2 different amounts of money on the stamps, or 3. Frobenius coin problem is the same, where instead you think about it, if you only had 2 kinds of coins, maybe you only had a 7-cent coin and a 10-cent coin, what can you make? By the way, this is why we don't have countries that have 7-cent coins and 10-cent coins. Because the big question here is, what numbers can you make and what numbers can't you make? What can you make? There is a formula for what kinds of numbers you can make. In particular, the largest one you can't make. But I'm more interested in looking at the pattern and the graphical visualization of what you can and can't make. So for that, I want to draw a diagram. I have 2 kinds of boxes. One is 7 and one is 10. And also, I am going to say, let's draw a table of all the possible amounts of chicken nuggets that I might want to buy. I'll start by putting 0 on here. Again, I'm starting all my things with 0. It's very convenient for number theory. Maybe I want 0. Maybe I want 1. Maybe I want 2. Maybe I want 3, 4, 5, 6, 7, 8, or 9. Okay? Or maybe I want 10. I'm showing you how I'm systematically drawing all the numbers in a table. 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. You may say this can take very long to draw this table. And that's why I drew this table with exactly 10 across. Because I can tell you the next row of this table is just 20, and all of these are going to be whatever those would be. And I'll even draw the table with lines instead. So what I mean is that I will draw the table this way. This is a time-saving way to do a problem like this, which I'm going to share with you, because sometimes if you're trying to think about what's happening to lots of numbers, it can be useful to find a way to write this down where you don't even have to write all the numbers. Because now that I've written this, you understand that in this square is 26. So I don't even need to write that 26. Here's 30, 40, 50, 60, 70, 80, 90. And I'll finish this table. This is the fastest way to draw all the numbers from 0 to 100. Okay, now, I have all of this written down. These are all the numbers of chicken nuggets that I might want to buy. I actually also drew these where it was 10 across on purpose. Because, let me think about what are the different kinds of numbers of nuggets I could order by thinking about what boxes I'm using. What if I use no boxes of size 7? If I use only boxes of size 10? Well, if I use no boxes of size 7 and only boxes of size 10, I can make any of these order sizes, including 0. So I'm going to color these in like this. I can get anything in this column, starting from the 0 down. I can do all of these by using no 7s. So if I use no 7s, this is the only thing I can make. But I can use boxes of 7s. What if I use exactly one box with 7? Only one 7? Well, then in that case, that lets me get anything here. I can then get anything in this column. This is what happens if I'm allowed to use 1 7. Okay? The 1 here is not the same as the 7 there. The 1 is counting how many, and the 7 is a kind of box. I can make any number of these nuggets. Well, what if I can use 2 7s? If I can use 2 7s, now I can get from 14 onward. This is now interesting. Look at this column. This column does not include the 4 up there. It only starts from the 14, which I'm already going to write down here. This is what happens if I use 2 7s. It starts from the 14 and it goes down forever. What if I can use 3 7s? If I can use 3 7s, then it's going to start from the 21. And it will go down forever. This is what happens when I can use 3 7s. And I'm emphasizing that my 3 and my 7 are different kinds of numbers. So that's no 7s, 1 7, 2 7s, 3 7s. Well, there's a 4 7s also. 4 7s is going to start from 28 down, which is going to be here. This is 4 7s. This is 4 7s. You may start to notice an interesting pattern. As soon as I find a number, I can do the whole column that goes forever down. Also, you may notice that I seem to always be going into a different column. Let me write those observations down. Once I touch a number in a column, which is by taking 7 times something, then I can get the rest of the column. That's one observation. But the other big observation that looks pretty interesting is that I am not hitting the same column twice. Seems like I don't hit the same column twice. At least not yet. Let's see why that second one is true. So the first one is obvious. Once I touch one, I can keep adding tens. That's obvious. For the second one, why is that true? Because the second one, what's actually happening is that the columns that I'm touching are like 7x mod 10. And as we've seen from other lessons in this mini course, 7 and 10 are relatively prime. 7 and 10 are relatively prime. So what that means is that if I take 7 times 0, 7 times 1, all the way to 7 times 9, these will all be different. These are all the residues modulo 10. So if these are all the residues mod 10, each taken exactly once, that's why I'm not hitting the same column twice. Let's go back to the original picture, because that's how we can find out what kind of chicken nuggets we can get. That was 4 sevens at the 28, and it will take me some time, and eventually I will touch every single one of these residues. Which one do I touch last? Well, the last one I touch, this was 7 times 0. Then I have a 7 times 1, 7 times 2, 7 times 3, 7 times 4. The last one I will touch is 7 times 9, which is 63. So the last one that I will touch right here is 7 times 9. And once I have that number of chicken nuggets, which is with 9 boxes of 7, I will have everything below it. But that's also the last one. That's very special. This is the last one, the last column that gets cleaned, that lets me take the rest of them. By the time I get to this, let me just finish the picture. By the time I get to this, all the rest of the columns will be filled. I did 4, so 5 will be 35. 35 is here. 35 starts from this. And then after that is 7 times 6, 42. 42 will be this. Then I have 49. 49 will be this. Then after 49, I have 56, which is this. And you really do see that the last column to get hit is 7 times 9. Why is this interesting? What this means is that after 7 times 9, from that point on, I will be able to get any number of chicken nuggets I could possibly want. The only issue is if I ask them for some strange number like 19, then I can't. But if I want to know what is the last number, what is the biggest number of nuggets that I cannot buy, the last empty space in this table is here. This is the last empty space. What is that? We're going to have a formula for that now. This is the biggest number that I cannot make out of 7s and 9s. Biggest number that I cannot make with, 7s and 10s. The biggest number I cannot make with 7s and 10s is going to be the one right here. It's 7 times 9 minus 10. Now, I could calculate what that is. That's not that hard. This is 63 minus 10 is 53. But more interestingly is, what if they weren't boxes of 7 and 10? What if I had two different sizes? Suppose I had boxes of X and Y. What if the boxes of nuggets were x and y. Now I would like to find a formula that gives me the 53. Well, what's so special? Well, two things I need to say first. If x and y have a common factor, then there are some numbers I will never be able to get. A little comment that's very important here is that if x and y have a common factor, you're going to miss infinitely many numbers because all nugget sizes will have that common factor. All combinations will have that factor. So there will be infinitely many not possible. But if x and y actually are relatively prime, then we can see where this comes from. Let's look back. Why do I have 7 times 9? Maybe I should call one of them x and one of them y. Well, I was talking about boxes of 7 and 10 before. So if my 7 was my x, what is my 9 really? What is happening is the 9 is, it goes from 0 to 9. So 9 is y minus 1. Because what I'm doing is I'm taking 0 x's, 1x, 2x, all the way to y minus 1 x's. But after I've taken all of those, then to find the last one I cannot get, I go up by 1 row. That's minus y. So this gives you a formula which you may have learned in school or you may see at some point. The largest number of boxes, or the largest number of nuggets that you cannot order is just x times y minus x minus y, which is now easy to check. 7 times 10 is 70. 70 minus 10 is 60. 60 minus 7 is 53. Done. Yes, we could do the question very quickly just by knowing the formula. But I wanted to share with you the entire picture, because then you can see that this problem, if you draw the rows and columns right, you can see exactly why the last number that you cannot reach is directly above right there.